Welcome to Maths with EJD. In this video, I'll be talking about cutting plane solution to an integer linear programming problem. In the previous video, I had given an overview of the cutting plane method for integer linear programming. So here I'm solving a specific problem, and this is the problem statement. Or let me just call it problem setup. Um, so we have to maximize z equals, so it's the same problem I solved uh using the branch and bound method, you know, so it's the same problem. So let's see how we can get the same solution using different methods. So maximize z equals 3x plus 2y subject to x plus 2y less than or equal to 5.5 and 2x minus y greater than or equal to 1, and again x comma y is greater than or equal to 0. But since it is integer linear programming, integer is the key. So you have x, y again are both integers. You know, that special z is indicative of the set of integers, basically. Okay, so their x and y are required to be integers, so that's the way to go. Now, as I explained in the previous video, right, I told you that the first step you take is to solve the LP relaxation, the linear problem relaxation. That is the problem that ignores this part where x and y must be integers. So that's what that is. So, and in that case, it means we have a problem as this: maximize z equals 3x plus 2y subject to x plus 2y less than or equal to 5.5, and then 2x minus y greater than or equal to 1. So x comma y are both greater than 0. So this is not like a normal linear programming problem now without the integer, because we don't care any longer about integer. And to solve this, right, you can use graphical method, you can also use simplex method, but graphical method is more straightforward, so I'd rather go for that. And of course, it's the same thing I did using the branch and bound method. So I'll just go straight to Desmos. Okay, I don't want this. So I'll just go straight to Desmos and then just plot the constraints. So we can then we get the corners, and then that will give us, then we evaluate the corners to see which of them gives us the maximum value. So x plus 2y is less than or equal to 5.5, first thing. Secondly, 2x minus y is greater than or equal to 1. Well, for the first time, right? For the first time, I didn't usually put x greater than or equal to 0, the non-equality constraint. So I'm putting that for the first time. Then I also put y is greater than or equal to 0. Okay. Yeah, so I mean, maybe it has just made it complicated. I guess I should just remove it. We already know that the region we are interested in is where the two intersect, and that is this small triangle you're seeing. So what we are interested in is, of course, we know it cannot go negative. So we are interested in that corner, which is 0.5. We're interested in that other top, which is 1.5, 0.5, 0, 1.5, 2, and this corner, which is 5.5, 0. So those are the three corners that we see from the point from that where the two regions intersect. That will be the feasible region. All right. Of course, it also extends down, but it will be negative. So it goes down all this way. So, but we won't bother about all that because because we have the non-negativity region, the non-negativity constraints. So we have 0.5, we have 0.5 comma 0, we have 1.5 comma 2, and 5.5 comma 0. So we go back to what we have, right? Um, so let's extend this back. All right. So I can say, so now we are talking about solution, right? So let me just say graphical solution, graphical solution. By plotting the constraints, by plotting the two constraints, So you saw how I plotted the two constraints on Desmos. Normally, I explained how to do that manually in a couple of videos. So you may want to revisit that. These are the two constraints now. So by plotting the two constraints, we obtain we obtain three corners, three corners of the feasible region, three corners of the feasible region. Okay. And they are basically what I can call A 0 0.5 comma 0. B is 1.5 comma 2, and C which is 5.5 comma 0. Okay. So, but we want to know which one is the maximum. So, it was the constraint we plotted. So now to know the maximum, we have to use the objective function, which is Z. So uh to find the maximum, to find the maximum, we evaluate the objective function. We evaluate the objective function at each point, point, at each, if you like, corner point, at each corner point. Okay. So we already know that Z is 3x plus 2y. That's what the problem, that's what we have in the original problem. 3x plus 2y. That is what Z is. So if you now have ZA, so ZA is actually evaluating Z at 0 0.5 comma 0, and that is 3 times 0 0.5 plus 2 times 0. That is 1.5 plus 0, which is finally 1.5. So we have 1.5 for that. Then we have ZB, which is Z evaluated at 1.5 comma 2. That is 3 times 1.5 plus 2 times 2. So that is 3 times 1.5 is 4.5. The 4 is looking awkward. So 4.5 plus 4, and that is 8.5. That's ZB. And ZC is Z evaluated at 5.5, comma 0. That is 3 times 5.5 plus 2 times 0. 3 times 5.5 is 16.5 plus 0, and that is 16.5. So from all indications, right, ZC, which is equal to 16.5, presents the maximum value, present the maximum value. Okay. So we can say, therefore, therefore, the optimal solution is X equals, the one that gives you the optimum, that X equals 5.5 and Y equals 0. So X equals 5.5, Y equals 0, and Z is 16.5. This is actually the optimal solution, right? But then we are solving an integer linear programming problem. So this is not required, this is not expected to have that fraction part, okay? It is not expected to have the fraction part. So, but this is the first step towards getting what we are expecting to get. And this is step one, right? Step one is to solve the LP relaxation. Now that we have solved the LP relaxation, we have found a an optimal solution, normal optimal solution, if you're not worried whether it should be integer or not. So now we go for step two, which is to introduce a cutting plane. Introduce a cutting plane, or simply introduce a cut. Okay. You can just say introduce a cut. A cutting plane is actually a cut, right? So we can say here that since x equals 5.5 is fractional, it is fractional because it has a decimal part, this 0 0.5 part. So since x equals 5.5 is fractional, we need to introduce a cut. We need to introduce a cut to exclude this solution, okay, while maintaining the feasible region, for integer solutions, because we are interested in just integer solutions. Okay. Okay. So basically what we're just going to do is this. Let me see. Well, I don't want to. One way to derive a cut is to look at the fractional part of the solution. Here, x is 5.5, and it has the fractional part of 0.5. So we can create a cut based on this fractional value. So we can use a Gomori cut or Schwartz Gomori cut, but for simplicity, let's assume that we want to exclude the fractional solution. So we want to exclude the fractional solution by adding a constraint that eliminates fractional values for x. So this can be done by noting that. So we already know that you know, x is 5.5, right? So a simple cut, a simple way, a simple way to cut, a simple way to cut is to add, is to add the inequality, is to add the inequality. X is less than or equal to 5. So you see, the 0.5 part, we throw it away because we don't need the fractional part. We also have the option of saying X is less than or equal to 6 because it's 5.5 lies between 5 and 6. So it's, I mean, that bears a close resemblance to the branch and bound method. So, but the easier one is to just say X equals 5. So that way we know that whatever happens, the worst case scenario, x will be 5, right? So this cut excludes the fractional part, x equals 5.5, because now any solution for x must be less than or equal to 5. So a simple way to cut is to add this inequality. So so we are going to, this is the cut we are going to add now, right? And it takes us to the next, to step 3, because we know the cut to add. Step 3 now, we now solve the new solve the new LP with the cut. Okay, solve the new LP with the cut. What that means is we have a new problem, maximize, not totally new. Z equals 3x plus 2y subject to subject to all the normal constraints, x plus 2y less than or equal to 5.5, then 2x minus y greater than or equal to 1, and then x is less than or equal to 5. So you see, this is the cut now. This is the cut we have added. And then, of course, we know x, um, x comma y, x comma y are greater than or equal to 0. So in this case, of course, we already know our plan is to take it all the way down. Okay. Um, so we not want to solve the new LP with the cut. And let's see, since I was already using graphical method, so let's just continue with that. So, I mean, we have our normal regions, right? The only thing now is that we are now going to have x less than or equal to 5. So if we add x less than or equal to 5 to it, so you see that the corners will change. So this is, we now have this corner, this corner, this corner, this corner, this corner up here, right? And this corner down here. Okay. So we have 5 corners now. So those 5 corners, so because of the x greater than or equal to 5 now, we now have 5 corners. We have 0.5, comma 0. We have 1.5, comma 2. We have 5, comma 0.25. And we have 5, comma 0. So you can see we have four corners now. So with those 4 corners, then we go back to this problem we've been dealing with. Okay. So you can see that that cut has added a new corner. So um, from from the graphical method, from the graphical method, we now have we now have four four corners. We now have 4 corners with the introduction of the cut. With the introduction of the cut. So what I'm just going to do here is that I'll just maybe I should tabulate it to make things a bit uh, a bit nicer. So here we have corner. Okay, we have the corner. For instance, a 0.5 comma 0. Okay. Then what else should we have now? We have the corner. Of course, we already know that the objective function is 3x plus 2y. Then we have the objective function value. Yeah, let's call it that way. Objective function value corresponding to the corner, right? So that means we have ZA to simply be 3 into 0.5 plus 2 into 0. So that is 4.5, right? That's actually 1.5, sorry. That's 1.5 plus 0, and that is 1.5. So we have this. Then we have B. B is 1.5 comma 2, just like what we had before. So ZB now is 3 into 1.5 plus 2 times 2. That is 4.5 plus 4, which is 8.5. We have this. Then we have C now. C is 5 comma 0.25. So that is ZC. ZC is now 3 times 5 plus 2 times 0.25. That is 3 times 5 is 15. 2 times 0.25 is 0.5. That is 15.5. So lastly, we have okay, I mean this this C, right? This C cannot hold water, right? This C cannot work. Okay. This C, we cannot take this. Okay. We can't take this because uh y is 0.25. It's not an integer, so it's out. So we can't take that, right? Um, because we need integer for both x and y. So now we have d. So I shouldn't even have bothered with that. So d now is 5 comma 0. So that means zd is equal to 3 times 5 plus 2 times 0. That is 15 plus 0, which is 15. So at the end of the day, this 15 is the biggest, okay? So this 15 is the biggest. So so the optimal solution is that such that x is equal to 5, y is equal to 0, and z is equal to 15. Z is equal to 15. Now with this now, you check again. Is everything integer as expected? X is equal to 5 is an integer. Correct. So we have excluded the 0.5. Y equals 0 is also an integer. So Z could actually be anything. We don't care. So as far as X and Y are an integer, we are good to go. So with this now, we can say that we have found a solution because we don't have to, we no longer have any fractional parts to which will give us any trouble. So um I mean, there's no cut to add anymore. So we have basically come to the end of this because we have got our final solution. All right. So if you have not subscribed to this channel, be sure to do that right away and hit the notification bell so you can always get alerted each time a new video is released. Also, comment. Let me know if you want me to solve a problem or teach a topic. Then like and share so that more people can have access to this great content. But by the way, if you still have any if any of the answers at this point is still fractional, then we'll keep adding cuts like that until we totally get integers, right? So if you have not watch out rather for the next video where I'll be showing you the Python code for what I've just done here. Till then, have a great time. Bye.